So we talked a lot about how igneous rocks are formed last time. We looked at that in lab. The whole issue of how we actually get earth materials to melt to produce a magma to begin with. What are the stages in recrystallization of that material to form the various classes of igneous rocks. So that's more kind of like on the small scale, looking at particular rock samples. Here we want to look at how do these igneous processes manifest themselves on the landscape. And so this slide pretty much summarizes what we're going to cover for the next 10, 15 minutes or so. We have talked about rising magma chambers coming up, and we'll talk more about actual volcanic eruptions later. But there are essentially different kinds of ways that magma can be converted into igneous rock below the surface, in which case we're talking about what kinds of igneous rocks? See, there's some examples or the general name of the type of rock, igneous rock that forms underground. Plutonic or intrusive? And what actual kinds of rock types would we expect to see? Larger crystals, so granite is one that we looked at. What? Diorite. Gabbro. So this is the more felsic part, this is the more mafic, and diorite is intermediate. Okay. So if the magma never breaches the surface, eventually it will cool off. Cools off more slowly, of course, that's why we get the large crystals. And you get different kinds of structures depending on where the magma has been able to get to. Either to the magma chamber or above before it actually breaches the surface. So, clearly we've got the magma chamber itself, and if the magma source eventually gets cut off, that magma chamber will eventually cool off. The whole magma chamber itself could solidify into a batholith. We have the ability for magma to move up through fissures and cracks in the rock, and eventually can go up into the neck of a volcano. It's still magma at this point because it hasn't reached the surface. If the source gets shut down and cooling takes place over long periods of time, any or all of these passageways can eventually get converted into recrystallized igneous rock. And so we basically have batholith for the magma chamber itself. Sills and dikes would be how these trails of magma through the rock layers get solidified, and then volcanic neck is hopefully pretty straightforward. The magma got up into the conduit of the volcano, but actually didn't get erupted out, eventually crystallized in place. Unpack some of these in a little bit more detail. So here's just a closer view. Dikes essentially and sills are very similar. It's just that sills follow the separations of the strata. They don't cross the pre-existing strata of rock, whereas dikes are cross-cutting structures, as we've looked at before. Okay. So there are a few actual extinct hollowed out magma chambers that geologists can get down into. It does not look like what Brandon Fraser saw on Journey to the Center of the Earth, if any of you saw that movie. Jules Verne in the original story and clearly in any of the movie adaptations didn't really have an accurate view here. This is an ancient drained magma chamber in Iceland. If you just look at it, there are all sorts of rocks and so forth we'll look at, and all of this rough edge of the magma chamber where the crystallization had happened partially before the magma drained down. Okay. So there's lots of things that actually happen in magma chambers. We've got this magma coming up from deeper in the lithosphere. Again, the magma has to rise faster than it cools in order to maintain that decompression melting of the magma. But as it's coming up, it's going to be going through all sorts of surrounding rock. And as it does so, if you've got hot molten rock coming up through rock layers, what's going to happen to the rock layers that the rock is coming up through?
They're going to melt.
Parts of them are going to melt, or if parts of them don't melt entirely, parts can fall off into the melt, and then the remaining surrounding rock can be altered by the high temperatures and pressures from the magma to form metamorphic rock, as we'll talk about later. So, as the magma is rising up through this surrounding rock material, its composition is going to change as it's picking up material from the rock it's going through. And if we're talking about more of a basaltic, a very mafic magma coming up from deeper in the lithosphere. If this is coming up through continental crust, the continental crusts tend to be more felsic. And so the migration up through the surface layers provides an opportunity for the magma to pick up more felsic material, higher proportions of silica. So xenoliths are these examples where the magma's come up and basically has knocked rocks off of the surrounding area. The magma at that point may not be hot enough to completely melt these rocks that are falling into the melt. And so you see these xenoliths showing up as very distinct rock and mineral compositions in a surrounding matrix of magma. So, we saw some xenoliths when we were hiking around Sunset Crater, looking at those lava flows. There are possibilities for different magmas to come together and form a new magma composition. You've got white cake batter and chocolate cake batter, and you mix them together. Obviously, you're going to get some mixture. This just shows it can be kind of wholesale mixing of two different magma masses, or sometimes there might be a pathway in the rocks that these magma bubbles are coming up through that would allow one of them to kind of inject material into the other. And finally, there's going to be a lot of effect on the composition of the magma as what's going to be happening to the temperature and pressure of the magma as it's rising through the surface layers of the Earth. What's,
The temperatures can decrease.
and the pressure,
Will decrease.
both will decrease, okay? So as those temperatures decrease, what's going to start to happen in the magma? Yeah, the minerals that have the higher melting points, and therefore the higher temperatures at which they begin to recrystallize, they're going to start to crystallize out. And those are going to be things like olivine, for example, which is going to pull out, a certain amount of silicate tetrahedrons and a certain amount of iron and magnesium. And if those materials are going into the small crystals of olivine that are beginning to form in the magma as it's starting to cool off, clearly those are going to be taken out of the melt, and the composition, the balance of materials in the melt is going to change over time. So you can see that here we've got partial melting of the surrounding country rock. We've got partial initial crystallization of minerals. Those early formed crystals are going to tend to be denser than the surrounding melt. They're going to naturally tend to fall to the bottom. There's going to be more crystallization that's going to be taking place around the outside of the magma chamber, because against that surrounding country rock, that's going to be the place where the cooling off is taking place. And the composition of the magma that's left in a molten state is going to be continually changing over time. This is just showing this with little yellow crystals and red crystals. So, if we begin with a melt that is fully molten, all of the elements are going to be dispersed throughout that material. If the initial crystals begin to suck up more of the yellow than the red, clearly what can you say about the magma that's remaining in the molten state in terms of its red to yellow balance? It's going to be more red in it, yeah. Okay. So it's a lot more complicated what's going on in the magma chambers than what we typically would model in the lab. You've got varying rates at which cooling off is taking place. You've got who knows what kind of rock the magma is coming up through. You've got continual melting of country rock and crystallization of minerals out of the melt as it starts to cool off. And so the eventual composition of the magma that's left over is just going to be quite variable. Okay, so let's just run through some of these structures. I've already mentioned them. Batholith basically refers to huge masses of plutonic igneous material that basically represents large magma chambers that just kind of stopped dead in their tracks, eventually cooled off over time, and form these massive structures. And with future erosion, if overlying layers of material eventually get eroded away, these batholiths or stalks, which would be the smaller bits of batholith, will eventually be exposed at the surface. This would be very well consolidated igneous rock, large crystals, well interlocked. It's going to be fairly resistant to erosion. And so if you had, say, layers of sedimentary rock on top of this, those sedimentary rocks in general are going to be more easily eroded away. And then, over time, that will expose these batholiths. So this is Half Dome, right, in Yosemite. one huge mass of recrystallized igneous rock. At one point, this was underground. Magma chamber crystallized and eventually was uplifted, and the surrounding overlying materials eroded away. The Black Hills are also a huge series of batholiths from, and yes, you guys recognize this place? Okay. Mount Rushmore basically was carved where it was because you have this, extensive, solid, essentially piece of rock that can be carved, sculpted on a huge scale. Here's Crazy Horse, a nearby batholith that has been for the last several decades slowly been worked on to create a statue to that Indian leader. And here's Stone Mountain in Georgia, basically another huge chunk of igneous rock carved with the silhouettes here. Okay, so then we're talking about dikes and sills, and again, sills are concordant in that they follow the pre-existing layers of the rock, whereas dikes are going to be cutting across. Now, they don't, dikes are oftentimes displayed as these right angle fractures through the pre-existing layers, but they don't necessarily have to be at 90 degrees like that. So this material here, you can see it's cross-cutting these pre-existing layers of sedimentary rock. This is, essentially igneous material that had been forced across those layers and then solidified in place. They're tabular in that they form these fairly uniform widths of material that are either going along or cutting across the grain, so to speak. So here are just different examples of dikes. It's clearly, it's hard to see the lights on. So you certainly have, there we go. You can see that this material is quite distinct in terms of its composition from the background material that it cut through. Same thing here, and so forth. Here's a sill. So why is this sill not completely flat, as is generally depicted in diagrams? How can you tell that this is a sill? Since this is at an angle, how can you tell that this is a sill and not a dike? Grace?
It's parallel to the other mountain.
Okay. So it's parallel to the other. So either this was nice, flat, sedimentary rock layers, and then the igneous material got forced in between, and then the whole thing got uplifted in such a way that all the layers got bent. Or it could have been that the sedimentary layers were initially deformed, but still provided a concordant space for later igneous material to come through. So, going back to our earlier discussion about relative dating, if you didn't realize that this was a sill, what would you expect to be the relative age of this igneous material versus this sedimentary material below it? Which should be younger, which should be older? Well, 1 here, 2 here. Two should be older. Okay. It's more of a question about this sedimentary material above. Okay. If you didn't know that this was a sill, what would your expectation be about the relative age of 3 versus 1?
1 would be older.
You would think 1 would be older. I mean, 3 is clearly older than 2. 3 is younger than 2. 2 is older than 3. 2 is older than 1. By simple superposition, you might expect that 1 would be older than 3. And so it's important to actually recognize when you have igneous material that's been kind of intruded into pre-existing layers. Otherwise, you're going to get confused about the relative age.
Well, couldn't you, I might be misinterpreting this, but the lighter patch on the upper side, bottom side of the sill, is that a little bit of contact metamorphism?
It is. And that's how you would tell. If we've got 2 different scenarios we can think about here. We could say that all of the lower layers of sedimentary material, including layer 2, were laid down before. And then you could have had a lava flow on the surface that would be on top of that. That would be our number 1. And then we could imagine that subsequent sedimentary layers could be laid down on top, and that would be our number 3. Versus, we have these sedimentary layers laid down, and then later we've got the igneous material coming in, and so it's actually a later layer than either 2 or 3. A couple of ways to recognize this would be, the hot material that's being forced basically between these layers is going to lead to some amount of metamorphizing of the surrounding layers of rock. And for there to be contact metamorphism on top means that layer 3 must have been there when the hot magma came through. If we had this situation, the hot lava flowing over layer 2 might lead to some contact metamorphism at the top of layer 2. But then the lava would have been cooled off, and later sedimentary layers would have been laid out on top. There should be no contact metamorphism above that igneous layer. You can also tell presumably by the type of igneous rocks that's in that layer 1, whether they're plutonic or volcanic igneous rock. I mean, is it granite and gabbro, or is it basalt and rhyolite? And if it's granite and gabbro, then obviously it's not being laid down on top of the surface. I don't know if any of you recognize this. How many were familiar with the Palisades along the Hudson? I'm pretty sure that's where I got the picture from. But yeah, this would be a possible place for us to go look at igneous landforms, but we're going to go to central Connecticut instead. But if you're ever down by Yonkers and look across the river, you'll see essentially these large columns of igneous rock that were laid down as part of this part of the events we'll talk about later. Okay. Just another term for you to know, we have a laccolith is sort of like a dike, but how is a dike different than this laccolith?
It's discontinued.
What?
Discontinued.
Not the dike. This could be a sill. I mean, a sill is also following the layers, but a sill, how would a sill and a laccolith differ?
The sill is parallel on
Yeah.
both sides, laccolith is parallel on the bottom.
Yep. So that sills and dikes tend to be tabular structures, which mean basically kind of parallel sides. And here we have kind of this half dome that, presumably had been in the past laid down underneath these pre-existing layers, which have since been eroded away. Okay. Volcanic necks are kind of interesting structures. Oftentimes you see this columnar jointing as the magma cools underground. When the magma does solidify, is it going to expand or contract, going from molten to crystallized phase? It's going to contract. So as you have this big mass of magma that is slowly cooling off and crystallizing, as that mass itself begins to contract, it's going to lead to various stresses in the solidifying material. And generally speaking, these will oftentimes these columns will separate out from the surrounding columns as kind of fairly hexagonal structures. And I'm not sure if we'll see any of that on Tuesday or not. So Giant's Causeway in Ireland, Devil's Postpile, probably the most famous jointed columnar jointing in a volcanic neck that in the U.S. is Devil's Tower. And I don't know, that movie's pretty old now. I don't know if any of you have ever recognized it. E.T. Thank you. So it's actually a combination of a solidified volcanic neck over a batholith. So at one point, this would have been a volcanic structure that is sticking out of a much higher layer of material. The magma chamber would have been underneath, would have had, in this case, a fairly huge conduit that's feeding the volcano. When the heat basically got shut off on this system, the magma chamber and the conduit crystallized, forming this batholith and volcanic neck structure, and then all of the surrounding material eventually gets eroded away, leaving this stuff behind. So why is this stuff left behind as erosion is taking place? Again, very much more resistant to erosion. And this just to show you that Devil's Tower is part of a huge batholith series out in this region. South Dakota primarily, northwestern South Dakota, and so imagine in the past a much higher surface layer in this area a large amount of underground magma activity, multiple interconnected magma chambers. Eventually, the heat gets shut off to this whole system. It slowly cools off, and then these structures that are sticking out are the remnants that we see. So some fairly striking structures, I think. These different sills and dikes and batholiths. Basically, one of the important ways that these plutonic processes eventually get expressed on the landscape. Now, as we talked about in that rock cycling paper that was looking at trying to quantify rates of different parts of the rock cycle, again, most of our land surface is not this stuff. What's the most frequent rock type that we see at the surface of the Earth? Sedimentary. So when you do have these things sticking out and about, they're pretty striking and noticeable.